All right, welcome to Doozer Shop. Then the Colchester lathe is still on the docket, repair. Last time we did the repair of the, I showed you the finished repairs on the power feed for the lathe, the power feed, and the apron, and I've been I've been smiling for days how successful that was. I can spin the feed rod by hand. No binding in either direction, whether it's the bed feed or the cross feed. It's just fabulous. So adding those, I guess you'd call them stops or whatever, to the rear of the rocker box, and it stabilized the motion. It locked it in, the motion of the rocker box, so it doesn't bind on the feed shaft, feed rod. Like I said, that's kind of a factory design flaw. Us engineers, we don't get it right all the time. And I studied the evolution of the Colchester, of this series lathe. I think this lathe is a 1976, mid-70s, let's say. And you could see they had the 13-inch, the 15-inch, and the 17-inch, and they had a smaller one, the Student or something, I forget, 12-inch maybe. But the power feeds, I've been looking at Tony Griffith's website. He's got lots of cool pictures of these lathes, and great site, you should check it out. The apron and the modifications that were done when they increased the size of each lathe. And even I think it was the 15-inch lathe suffers from this, and it's even worse. There's like a plate, an angle plate, to absorb the thrust of the half nut for threading. And on the 15-inch, 13 or 15-inch, I forget which. Actually, I was on Facebook looking at pictures too. There's no angle plate to prevent the half nut from twisting, and I had a segment on the engineering of the twisting of the half nut on this lathe. So even their other smaller lathes there's engineering discrepancies there. Now Colchester fixed a lot of this in their next series of lathe. I think they called it, the square head, as opposed to the round head, speaking in general terms. They went to a true double wall oil filled apron. So this apron I have is not oil filled, and the other round head series is not oil filled. It's a double wall apron. Double wall means the shafts with the gears on them are supported with bearings on both sides, as opposed to a single wall apron, where the shafts are in a single bearing and they're cantilevered with the gears on them. So this is a double wall apron, but it's an open bottom, so there's no oil filling the apron. It's just oil from the top. Oiler ports dribbles down. It's a total loss system into the chip pan. So, but anyways, when they redesigned, Colchester redesigned their lathes to the square head, they had a full oil-filled double wall apron, and they changed the power feed mechanism design. They must have known that of the binding. I'm just assuming they must have known, because they redesigned it to the more modern apron that has been. So that new Colchester lathe, I think they called it the 1400 or the 1600. That's the RPM. I think that the top speed was like 1400 or 1600, depending on the size. And they had a 17-inch lathe too in the new series, but it wasn't. See, this is a 54-inch bed, and they made like a 78-inch bed. And the new lathe, the round square head series, is still a 17, but it's like a 60-inch bed. It's like some even increment number, but either way. So that lathe, I've got, it was copied by Chinese companies, Taiwanese companies, quite a bit. And what made that lathe so cool is that they call it the geometrically progressive speed levers. So it's got a dial within a dial, and I think it's like 12 speeds. You get 4 ranges with 3 selections within that range, or maybe I said it backwards. 3 ranges and 4 selections, I don't know. But the shafts are coaxial and the levers are about a common axis, so that's cool. And it is such a great redesign over these round head lathes. So many companies copied the Colchester lathe. I have an Acroturn 13x40 that's a rip-off of the Colchester. Select is the name of a Chinese company that ripped off the Colchester. Victor had a couple different Victor lathes. They also made a basically direct copy of the Colchester. Jet, everybody's heard of Jet. I'm sure Grizzly, and then there's that Matthews Precision or Precision Matthews. He imports lathes, some of which are just exact copies of the Colchester layout. So Colchester, they're right in the forefront of lathe development, and that series after the round head, the square head, it really stuck, and everybody knew so many modern features to it, they just copied it. And I think that's where the square head design that you see today is a big reason that everybody copies it. And you see it so often. Is this a good lathe? Anyways, one thing that they had in this next set of Colchester lathes, the square heads, was clutches, like motorcycle clutches in the headstock. Now, the motor could be running, and the clutches are, I believe, electrically engaged, which is okay. If you're going to have clutches, why not have a mechanical lever to engage the clutches? And the reason for that is if you have, for safety, if you ease a clutch in and you slowly start the chuck spinning, if you have a chuck jaw that's way out and it's going to hit the wing of the carriage or something that you just didn't see, I mean, you should spin your chuck before you turn the power on. Anyways, but if you don't, you just feather that lever just to make the chuck 1 revolution. That's why it's nice to feather clutches into engagement on a lathe. If it's an electric clutch where you just push a button, the clutch engages, kind of negates the reason for having a clutch. The only thing you're saving is you're leaving the motor running, you're saving a surge of electricity. Not a big deal. But yeah, clutches are good with a mechanical engagement. And not only to feather the spindle to see if anything's going to hit when you first spin it up. Also, if you've got something in the forejaw where it's offset, like a casting that's not going to be balanced, you can feather it up to see, are they going to shake or not? It's going to shake. And it just kind of gives the machinist a warm, fuzzy feeling that he's not going to have the work violently thrown out of the chuck when he hits the on button. So, good that they put the clutches in, bad that they didn't make them mechanical. I know old LeBlonds, old Monarchs, for them for sure. I'm sure the big ones like, Axelson and Sydney and American Pacemaker had clutches. But these big lathes and you could feather the clutch in. So that's kind of cool. I know I'm getting way off topic here with Colchester. But anyways, let's go handheld. I'll stop talking about Colchester in general. And I'll show you what I've been working on with threading dial. So let's check it out. All right, we got Jake and Elwood here over at the welding bench. Let me show you. This is the piece that I cut it off. It was brazed onto the threading dial on my Colchester. And as you can see, it was brazed together. It was a rough piece to begin with. These slots are cast in the mold. These recesses, I don't know if that's a metal saver feature or what, but all this is cast, nothing's machined. This bottom surface, this is the surface that bears against the apron as cast. So, not an expensively done part, very cheaply made. So you can see the braze, like I said, there's the joint, so the guy that did it, he did an okay job. You still see some voids in there. Lack of complete fill. And you can see the alignment, it's like crooked as a dog's ear. There's voids in the casting just from brand new. Look how crooked that is. But lack of fusion. I say at least they V'd it out properly, but they probably didn't use flux and they probably didn't clean it. But anyways, so that's the piece that I cut off, and you can see I just took an angle grinder and I cut it off. So I wanted to show you that. Let's go back over to the lathe and see how this was attached. Alright, I'm back here at the lathe. I'm going to take apart some of these Allen screws, and I'm going to show you what I got going on here. So you got to take this off. So this is the side bracket, of course, that I made to support the stops that register on the rocker box. So that's a block inside there. I'm going to take these off. Alright. So it fits kind of tight, so it gives us access to take off the thread dial. Okay. So you can see this plate, and it's all notched out. Alright, so that's for the threading dial. And you can see here that that's the bar where our feed dogs are part of there. And that's those two bolt holes, so I took the bolts out. So now we have the threading dial. So all I'm going to do is that I'm going to take that bolt out and loosen it first. Alright. Alright. So now I can take off the threading dial, okay? Alright. And here it is. Now, what the deal was, I can show you. Let me hold it like this. So, that was the old one. That's the new one. You can see, nice piece of steel, nice and flat. Let me show you. Let me just put it down and show you. Alright guys, got you back on the workbench with the threading dial. Kind of easier. Let me show you. Alright. So there's the threading dial. It used to be that, how am I going to do this? Like, okay. That's how this used to be attached to the threading dial frame. Alright, that's the old cast piece. I cut this off with a grinder because it was just so out of shape. So what I did is I made a new plate out of steel, 3/8 thick steel. This is some 1/4 inch or so piece of cast. And you say, you know, what's all this? Well, this is a piece of 1/8 inch plate steel, maybe just under 1/8, maybe 12 gauge, something like that. So I've got 1, 2, 3 sets of 3, 9 holes, and these screws are 632. I just kind of chose that size. I thought that was all I needed for strength, and then I had more of them to spread the load out, kind of like a riveted joint. Actually, I thought about using pop rivets on this, but either way. So it was sort of an evolutionary thing how I came to use these plates. I cut out a slot here. So let me show you from the side. So that's the side view of this threading dial. So it hooks over the lead screw, and the only way I think, I figure that's all about keeping the chips off the lead screw. Kind of neat. And the lead screw goes in here, and of course that's the gear that spins the thread dial. So this is the side that goes up against the chuck. This piece was on the other side. The mounting bracket is all cast. So you can see I surface ground this face. I squared this whole jobby up. I squared everything up. Surface ground the top of this. I indicated, so the top surface, you know, is cast. So I surfed around it with a plunger style indicator. And then I surface ground this. This side, like I said, this is the side where I cut the piece off, right? So that would have been Bazango. So this is where you can see that was right there. So now I got this piece. And the red is just a magic marker. So initially, there were 2 dowel pins in the lathe and 1 3/8 bolt. So now, instead of 1/4 inch dowel pins in the lathe, I got 1/4 inch set screws in there. And that goes in the holes in the lathe. I just thought it was a better deal to reverse that around. So anyways, you see on the back, it's going to just sit here for me, I have to hold it. There's a plate on the back, another 1/8 inch plate. So you can see there's 2 1/8 inch plates that sandwich the casting. And I got 632 nuts on the back there. So this slot where the gear is, this cutout slot is smaller than the front slot, because this one accommodates the whole. Man, doing stuff one hand is just like bam. So the back one is got that rounded out slot just to accommodate the gear, and it's smaller, and I forget what size I made it, and then the front one's bigger. So anyways, the back plate is wider than the front because it kind of goes to the edge of the casting, and this one comes on the inside of this rib. See, it's kind of like a decorative rib, strength rib. So this one, the rib has been cut off and ground off. And you can see there's brass at the top. I'm not taking all these screws out to show you guys. You can kind of just have to visualize with me. So I surface ground that rib to some flat minimum cleanup dimension, okay? And you can see there's a space next to it. But that's actually, that crack kind of goes diagonally around. You zoom out. So this comes down here, and the crack kind of goes where my finger goes, like that. The crack is in there. So this under here is brazed, and it was higher than the original surface. And I'm not taking this plate off, but everything is surface ground to this height. So the brazing, the iron, I had this on the magnet on the surface grinder, blocked in, and that surface grinder with that 46 J wheel, you can grind steel, iron, you can grind brazing, which is what the braze is, and it doesn't even load up the wheel. It's a good general purpose wheel for a lot of stuff. But so these three holes go through the surface ground part of the casting. These three and these three, actually I had put 632 washers in there. Let's see if I can. You can see the little shiny silver washers. Oh, there you go. So there's washers there, and there's washers. You can see. No, it doesn't like that. Come on. There's washers under there. 3 washers under there. And 3 washers under there. Okay. It's funny, this camera tells me I'm being shaky with my hand. How smart it is. So anyways, the thickness between these two plates ended up being right at like 3/16 of an inch. The thickness of the casting and the washers, and there's no washers on this side. So focus over here. So the piece of 3/8 steel, which I made the new extension bracket out of, I had to grind it down. I ground a step in it, as you can see, that fits in between the plates, which is 3/16, 188. And then I got the 2/4 20 Allen head bolts and nuts there. And of course, wants to. All right, so I got a plate on the back, a plate on the front. This new plate, which is that's the old one, that's the new one. You're gonna say, why is this milled down and pocketed in there? You have a flat surface here all the way, and this is actually pocketed 40 thousandths of an inch lower. Okay? Actually, I'm trying to zoom in. And forgive the red magic marker, I was doing some scraping. So that's pocketed 40 thousandths of an inch lower than the original surface. And the reason why, I will show you. So let's go over to the lathe. Alright, I'm back at the lathe. So the central bolt, right, That's a 3/8 tapped hole. So obviously this is the lead screw, this is the feed rod. These are the bosses on the casting that the bronze bushings are pressed into. So it's held by the central bolt. There's a hole there, you can maybe even see the bushing through it. And there's a hole there. So that's where the that set screw and that set screw go into them holes. There's the central bolt over there. So anyways, the central bolt locates in here. So these surfaces, so this pad and this pad were as cast, they were not machined flat from Colchester, right? Don't ask me why, I don't know. Also, this pad is 40 thousandths lower than that pad. Okay? This surface, if you put a, I was using not a file, imagine this is a steel parallel. If you put a parallel on here, that surface is lower by 40 thousandths. So what and also you can see, I know this is painted gray, where the red magic marker is, that's a fillet in the casting. It's a radius transition from this flat surface 90 degrees to this flat surface. And this fillet, it was so large, it was like a drunken fillet. It extended out into this casting pad. This one, the same thing. This fillet, you can kind of see the painted gray, extended, you know, out into this pad. So basically, you can see a chamfer there. This chamfer, and there's a chamfer on there, you know, is made to accommodate the fillet. You know, back to why is this pocketed down? So what this does, you can kind of see, that top pocketed out space touches up in there. Okay, and the bottom non-pocketed out, the flat piece, touches on the bottom. So to accommodate for this being low, I had to mill out a pocket in my threading dowel bracket for the top. So now it sits flat, and I had to scrape. That's why I got the red ink on it. I had to scrape all that. I'd put the plate up, rub it around, transfer the ink, scrape the high spots, clean it off, ink it up, do it again, rub it, look at the high spots, scrape it. I must have done this 10 or 12 times. But anyhow, this plate now fits on here very well. Absolutely, like, really well. Really good. Yeah. This took a while. Otherwise it would sit crooked. It would sit not flat, but crooked. An exaggeration. Let me put the camera down. Let me put this back on, and I'll show you more. Alright, so I'm going to take the threading bracket. It kind of hooks over the lead screw. And now this sits on here nice and flat. I mean, this thing is great. Up. Now it sits flat. You can Okay. Let me, now it's meshed in there good. I had to move the carriage. Kind of wiggle it. Alright, so now, if I move the carriage, see how the dial moves? Totally awesome. Okay, so that moves. This is all set. Let me put my side plate back on. And see how nice this fits in here. Once I move my hands, fits in there really well. So these attach the plate to the apron, these attach to that piece of bar stock that holds the stops for the rocker box. Okay. Let me tighten these first. Nope, wrong one. Just snug, snug. Alright, that's it. That's pretty stellar, in my opinion. Let me see here. So what we got here, make sure everything's backed up. All right, that's a beautiful thing right there. We got 2 1/8" plates of steel. We got a whole bunch of bolts and a whole bunch of washers. We have a transition plate. We've prepared the 2 surfaces, the mounting pads on the carriage, to be nice and flat. And you might see here that side plate. I had to extend that side plate where it's notched out lower. You can see the red faint magic marker line was the original cross surface, and I lowered it down 1/8 of an inch, and you can see that radius tucks right around the bottom edge of that threading dial, okay? So I'm calling that super successful. So like I said, that plate on the side of the apron is part of the power feed fix that you might see in the previous videos. But now I repaired the broken mounting tab on the threading dial, and we're good to go. So that set screw, I believe it's 1/4-28. It plugged a grease fitting hole for the bushing. Then I'm not going to grease this thing. No, that's just the wrong thing. So that was a grease fitting, a Zerk, if you will. And I plugged that with a set screw. So that's it. It took me about a weekend and another, say 3 days to fix this. Shop time. I am so happy with the way the threading dial fix came out, and I'm still ecstatic about the power feed levers and everything. I gotta put some oil cups. You might see some hose. I've been trying to figure out where I can put the oil cups for some bearings underneath there. So that's done. The power feed's 100% fixed. The threading dial, I am also ecstatic. Oh, and I don't know if I really did explain. It was sort of an evolutionary thing. The reason I chose 2 pieces of thin, like 12 gauge or whatever size that is, 1/8" maybe, plate, and to sandwich it between the two. It's just sort of a design evolution. It's a little bit flexible. Now, I mean, it's pretty stout, but I don't know. That mesh is perfect with the gear and the lead screw. I don't know if I can get the camera in there. Nope, I can't really get the camera in there. But the mesh is just very good to get everything lined up. See, that's the pain in the butt, is you're doing something like this and nothing is straight. Like, all right, these holes and everything that were drilled into the apron. Let me show you something here. Hold on a minute. Let me get my notebook. Hi. All right, so these numbers represent measurements of the central 3/8 tapped hole and then the 1/4 inch holes, top, bottom, and top. So the distance between these three holes, I mean, somebody was smoking crack. This is all over the map. So from the central 3/8 hole, threaded hole in the casting, in the bottom 1/4 inch dowel pin hole was 1.394 center to center, and then from the middle hole to the top hole was 1.273 center to center. So 1.394, 1.273. These are not, I mean, I got the decimal equivalent chart, and you're looking at numbers and you're trying to find an even fraction or an even millimeter or something to try and reverse engineer. What were these folks thinking, right? I don't know. I have no clue why these center distances are so jacked up. And then the vertical plane, they're not even straight in a vertical plane. I know we work off the center line, but I started working off an edge because that's where the straight edge kind of was easy to do the math and subtract out. So if you put a straight edge against the side of the 3/8 bolt and the side of the 1/4 inch bolt, it's 10 thousandths gap between the edge of the top 1/4 inch hole for dowel pins or whatever. But it's interesting that the side of this bolt and the side of this bolt were pretty much vertical. Now usually you work off the center line, but if you work off the side, the side of this hole and the side of this hole are vertical. I mean, that's just so weird because how can I explain it? Other than you work off the center line, and if the edges of holes are lined up, that's just weird. I can't come up with any words to say, then that's just weird. So if this is lined up at the edge of that hole, and okay, the reason it's weird is because, you know, if the holes are the same size, it makes sense. So the 1/4 inch hole there and the 1/4 inch hole there, they're almost lined up. So there's 10 thousandths off. But if the edge is lined up, the center line would line up. But if you have a 3/8 hole, or tapped hole in this case, there's no reason for the edge to line up. There is a reason for the center to line up because that's how standard stuff is made. But not on this lathe. This thing is just so wacky. Everything on it is just not lined up in any way, shape, or form that you would think it would be. So, you know, I had to go through and figure all this out, and you try to reverse engineer it by using common methods that any normal engineer would use to design something, because you know we all kind of think alike as far as engineers go. But this is weird. I don't know if it's because it's a British lathe and they just think odd compared to I don't know. But anyways, so, and it was odd that those surfaces, I'm tripping over my milk crate. Yeah. So I'm talking about that 1/4 inch hole for that, 1/4 inch hole for that, and that right there. So just to make that plate and to line everything up, and it wasn't even vertical, it was canted. I had to plumb it with a very precision level to get those holes back, everything vertical. So so I had to locate these holes again with respect to each other in the vertical axis and the horizontal axis, and then get the side of the plate to end up vertical. It's just such a, it's so weird. When you work on a machine, you really see inside the designer's head, and I see a little bit of chaos. Or like, so what else would explain it? Shoddy workmanship, a jig that was used on the assembly line to drill the holes with a power drill, like freehand, and the jig was off or something. I just don't know. But anyways, like the holes, these two holes in the apron are exactly 2 inches apart, and this hole, center to center, and this hole is exactly 2 inches from the center of the feed rod when I did all this in the milling machine. So when I design stuff, like these holes are all the 632 bolt holes. They're all a 1/2 inch from each other, and they're all in a line. That's how normal people do stuff. And there is a dimension between this line and this line and this line, and between these two sets of 3 is exactly the center of that shaft hole for the dial. Even though that's on an angle, right? That the hole for the shaft for the dial with the gear and all that is on an angle, but I still picked it up and I made the exact center of this, even though it's on a different plane, halfway between these two sets of holes. Anyways, that's it. I've talked too much about this, but it's interesting to get inside the head of the engineers that put this together. Anyways, happy the thread dial's finished. Enjoy. This is Doozer Shop.